Bismillahirrahmanirrahim. In this lecture, I am solving problem 6.16, last problem of chapter number 6 from the book Applied Thermodynamics by McConkey. So, the statement of the problem is a surface condenser is fitted with separate air and condensate outlets. A portion of the cooling surface is screened from the incoming steam, and the air passes over these screened tubes to the air extraction and becomes cooled below the condensate temperature. The condenser receives 20,000 kg per hour of steam. So m dot steam flow rate is equal to 20,000 kilogram per hour. Convert this into kilogram per minute, which is equal to 20,000 kilogram, and 1 hour is equal to 60 minutes. So which is equal to 333.333 kilogram per minute, and the condenser received 20,000 kilogram per hour of steam dry saturated at 36.2 degrees centigrade. So temperature of dry saturated steam is equal to 36.2 degrees centigrade. At the condensate outlet, the temperature is 34.6 degrees centigrade. So temperature of condensate outlet is equal to 34.6 degrees centigrade. Temperature of dry saturated steam is 36.2, and temperature of condensate outlet is equal to, this is 36.2 is, and Kelvin is 36.2 plus 273 Kelvin, which is equal to 309.2 Kelvin, and this is 34.6 plus 273 Kelvin, which is equal to 307.6 Kelvin. And at the air extraction, the temperature is 29 degrees centigrade. Temperature of air extracted is equal to extracted is equal to 29 degrees centigrade, which is equal to 29 plus 273 Kelvin, which is equal to 302 Kelvin. And the volume of air plus vapor leaving the condenser is 3.8 meter cube per minute. Volume of air plus vapor is equal to 3.8 cubic meter per minute. Assume constant pressure throughout the condensate. Pressure is constant throughout the condensate, and the condenser pressure is constant throughout the condensate. Calculate the mass of air removed per 1000 kg of steam. Number 1 required is mass of air removed per 1000 kg of steam, per 10,000 kg of steam, per 10,000 kg of steam. Number 2, the mass of steam condensed in the air cooled per minute. Mass of steam condensed. And number 3, the heat rejected to the cooling water. Now here are some constant values which we will use in the problem solution. R for air is 0.287 kilojoule per kilogram per Kelvin. R for vapor is equal to 0.4615 kilojoule per kilogram per. R is basically ideal gas constant. Molar mass of air is equal to 28.96 kilogram per kilomole, and molar mass of vapor is equal to 18.016 kilogram per kilomole. Now three temperatures are given to us: dry saturated state, condensate outlet, and T air exit, and both are in the saturated region. So we will find saturation temperature at for all temperature, because all this is, let's suppose this is TV diagram, temperature in degree centigrade, and V in volume in cubic meter per kg. So this is saturation curve. So all points are in this region, in this saturated curve. So in this curve pressure is constant. So we are finding for all temperature. High temperature is 36.2, second is 34.6, and third is 29. So all are in this region. At 36.2 this is dry saturated, but we know that dry saturated pressure is saturated pressure. Similarly here pressure is saturated pressure. Similarly in this part, this in condenser outlet here completely liquid, the pressure is saturated pressure. It means that we are finding saturated pressure at 36.2, 34.6 and 29 degrees centigrade. So saturated pressure, first we find PS. PS means saturated pressure at 36.2 degrees centigrade. So from saturated steam table, at temperature is equal to 36.2 degrees centigrade, but 36.2 is not available in the steam table. So pressure in kilopascal, temperature degree centigrade 35 is available and 40 is available in the table, but 36.2 is not. So we will do interpolation. At 35 degrees centigrade pressure is, this is 35. So at 35 degrees centigrade pressure is 5.628, and at 40 degrees centigrade saturated pressure is 7.384, and we have to find this one, pressure of saturated of vapor. We can also name this, it's PV at 36.2. So third minus first, 40 minus 35 divided by third value minus second value, divided by is equal to third minus first divided by third value minus second value, PV comma 36.2. PV is equal to PS, because this is pressure per vapor. So solve this and find the pressure. PV at 36.2 degrees centigrade is equal to 6.04944 kilopascal. Now we are finding saturation pressure at 34.6 degrees centigrade, which is equal to vapor pressure of vapor at 34.6 degrees centigrade, which is equal to, now 34.6 also not available in steam table. So from saturated steam table at temperature is equal to 34.6 degrees centigrade, but 34.6 is not available here, so we will do interpolation. Temperature in degree centigrade and pressure in kilopascal. So temperature 30 degrees centigrade and 35 is available, and we have to find the pressure at 34.6. So at 30 degrees centigrade, from the saturated steam table, pressure is 4.246. Pressure is 4.246. At this point it is required, and at 35 this is 35, 5.628, 5.628. So now we are doing interpolation. So 35 minus 30 divided by 35 minus 34.6 is equal to 5.628 minus 4.246 divided by 5.628 minus pressure of vapor at 34.6. So solve this and find PV at 34.6, which is equal to 5.51744 kilopascal. This is the saturation pressure at 34.6 degrees centigrade. Now P saturated at 29 degrees centigrade, which is equal to pressure of vapor at 29 degrees centigrade. So from saturated steam table, at temperature is equal to 29. 29 is not available in the table, so we will do interpolation. Pressure in kilopascal. Temperature 25 and 30 degrees centigrade are available, and we have to find saturation pressure at 29. So at 25, saturation pressure is 3.169. You can check here from the table. 3.169. And this is pressure of vapor at 29 degrees centigrade, and here at 30 this is 4.246. So do interpolation for this. So third value minus first value, 30 minus 25 divided by 30 minus 29 is equal to third value minus first value divided by third value minus second value. So PV at 29 is equal to 4.0306 kilopascal. So this is the saturation pressure at 29 degrees centigrade. Now we in solution in part 1, mass of air required value is mass of air removed per 1000 kilogram of steam. This is required in part 1. So as outlet temperature of air, T air outlet, it means that outlet temperature of air is equal to 29 degrees centigrade. So the partial pressure of air is equal to, so the partial pressure of air, we know that total pressure is equal to partial pressure of air plus partial pressure of vapor. So partial pressure of vapor is equal to partial pressure of total minus partial pressure of air. But air outlet temperature is 29, so we will use partial pressure of, this is partial pressure of vapor, sorry. Here is this. So partial pressure of vapor at 29 degrees centigrade, and total pressure is pressure at 36 degrees centigrade. Total pressure is equal to P total is equal to pressure at 36.2 degrees centigrade, which is equal to 6.04944 kilopascal. Because we know that absolute pressure is constant throughout the condenser. So putting values here, so pressure of air is equal to P total is 6.04944 kilopascal. This is P 36.2 degrees centigrade is P total because there is an assumption in the statement that the that the total that the pressure is constant throughout the condenser. So this is the total pressure which is constant throughout. So this is P total minus P vapor, minus P vapor is pressure of vapor at 29 is 4.0306 kilopascal. So pressure of air is equal to 2.01884 kilopascal. This is pressure of air at 29 degrees centigrade. Now we are finding mass of air. So M is equal to PV divided by RT. PV is equal to MRT. So M is equal to PV divided by RT. So mass flow rate of air M dot A is equal to P pressure of air multiplied by V dot of air, V dot divided by R of air multiplied by temperature. Temperature at 29, because here we use temperature 29 degrees centigrade, and the reason is T air outlet is 29 degrees centigrade. So and this is M dot, so this is V dot. M dot A is equal to pressure of air is 2.01884 kilopascal multiplied by V dot is given to us in the given data, which is 3.8 meter cube per minute divided by R per air is 0.287 kilojoule per kilogram, and joule we can write joule as Newton meter per kilogram per Kelvin, and Pascal is basically equal to Newton per square meter, and temperature of air is 29 degrees, which is equal to 302 kilopascal, 302 Kelvin, sorry. So this kilo is cancelled with kilo, Newton is cancelled with Newton, meter square and meter is meter cube is cancelled with meter cube, and Kelvin is cancelled with Kelvin. So this is kilogram per minute. So M dot A, and calculate the value, which is equal to 0.0885 kilogram per minute. But this is basically for 2000 kilogram per hour. Now required is to find the mass of air removed per thousand, and the calculation is per 2000 kilogram per hour. So now M dot A per 1000 kilogram of air, so as in 2000 kilogram per hour, which in kilogram per minute is 333.333 kilogram per minute. This is 0.0885 kilogram per minute. So in 1000 kilogram of steam, M dot is equal to, so per 1000 kilogram of steam, M dot per 3 3.333 kilogram per minute. The mass flow rate of air is 0.0885 kilogram per minute. So find this for 10,000 kilogram. This is not 1000, this is 10,000 kilogram. So kilogram per minute will be cancelled with kilogram per minute, and mass flow rate of air per 10,000 kilogram of steam is equal to, calculate this value, which is equal to 2.65 kilogram. This is the answer of part number 1. Now we are solving part number 2. So, and part number 2 required is mass of steam condensed in the air. Mass of steam condensed in the air cooled per minute. In the air cooled per minute. So we will use here molar fraction, mole partial pressure relation. Here we use mole partial pressure relation to find mass of vapor, mass flow rate of vapor at 34.6 degrees centigrade and mass flow rate of vapor at 29 degrees centigrade, because we can find condensed steam from the difference of mass flow rate. So inlet is mass flow rate at 34 and exit is 29. So the difference of these values will be the steam condensed in the air. So difference of these two values. So first we find these two values with the help of the mass and partial pressure, mole fraction and partial pressure relation. So this relation is a NV divided by NA is equal to PV divided by PA. NV is mole fraction of vapor. P is partial pressure of vapor. Na is mole fraction of air, and Pa is partial pressure of air. So we know that N is equal to mass divided by molar mass. So put here mass flow rate of vapor divided by molar mass of vapor. This is the value of NV. Divided by mass flow rate of air divided by molar mass of air is equal to PV at 34.6 divided by PV at 29 degrees centigrade. Now put values here to find the MV at 34.6. This is MV at 34.6. PV divided by this is PA. This is PA. So PA is basically, this is not PV. PA is basically P total. We know that P total is equal to P of air plus P of vapor. So P of vapor is equal to P total minus P vapor. So PA is equal to P total minus PV at 34.6 degrees centigrade. Now rearrange this equation. M dot V divided by molar mass of vapor. This is in double division. So in double division, molar mass of air divided by mass flow rate of air is equal to PV at 34.6 divided by P total. This is P total. So P total minus PV at 34.6. Now mass flow rate of V is equal to now write these values in on the other side. So this equation will become m dot v is equal to m dot a divided by molar mass of air multiplied by molar mass of vapor multiplied by PV 34.6. Rearrange the equation, P total minus PV at 34.6. So putting values, m dot of air, mass flow rate of air is equal to 0.0885 kilogram per minute divided by molar mass of air is 28.96 kilogram per kilomole multiplied by molar mass of vapor is 18.016 kilogram per kilomole. This kilogram per kilomole will be cancelled with kilo. So final unit will be kilogram per minute. And PV of 834.6 is 5.51744 divided by P total is 6.04944 minus 5.51744, and unit above and below are same, kilopascal and kilopascal. So kilopascal will be cancelled with kilopascal. Now simplify this value. So mass flow rate of vapor at 34.6 degree centigrade. Simplify this value. So this will be equal to 0. Finally value. This is simple calculation. Multiply these two and divide by this. Now subtract these two values and then divide numerator divide by denominator and then multiply these two values in. So the final answer will be equal to 0.57099 and unit is kilogram per minute. Now this is m dot v per 34.6. Now we are finding m dot v per 29 degrees centigrade. So use this formula. Just change the value from 34.6 to 29. So this is exactly the same, m dot of air divided by molar mass of air multiplied by molar mass of vapor multiplied by PV at 29 degrees centigrade divided by P total minus PV into 29 degrees centigrade. So use the above equation. Now m dot we putting values here. M dot of air is 0.0885 kilogram per minute. M dot mass flow rate of vapor is 18.016. Mass flow molar mass of vapor 18.016 kilogram. This is molar mass divided by molar mass of air is 28.96 kilogram per kilomole. So this kilogram per kilomole will be cancelled, and PV at 29 degrees centigrade is equal to 4.0306 divided by P total is 6.04944 minus 4.0306. Unit above and below are same. Here kilopascal and here pressure kilopascal. Kilopascal will be cancelled with. So final unit will be kilogram per minute. And simplify this calculation. So this will be equal to 0.1099 kilogram per minute. So mass of vapor at 34.6 degrees centigrade and mass of vapor at 29 degrees centigrade is calculated by us. So as we know that as the steam condensed and cooling the air the air is from 34.6 degrees centigrade to 29 degrees centigrade. So mass of air condensed, mass flow rate of air condensed is equal to mass flow rate of vapor at 34.6 minus mass flow rate of vapor at 29 degrees centigrade. So mass flow rate of vapor is 0.57099 kilogram per minute minus mass of vapor at 29 degrees centigrade is 0.1099 kilogram per minute. So mass flow rate of air condensed is equal to 0.461 kilogram per minute. So this is the answer of part number 2. Now we are solving part number 3. Heat rejected to the cooling water. Heat rejected to the cooling water. So we know that mass of steam N, which is given in the start of the problem, is 20,000 kilogram per hour. So convert this to kilogram per second. So 20,000 kilogram, and 1 second is equal to 1 hour is equal to 3600 second. So write 3600 second instead of 1 hour, which is equal to 5.555 kilogram per second. Similarly, mass flow rate of vapor at 29.6 is 0.1099 kilogram per minute. Convert also this into kilogram per second. So this is 0.1099 kilogram, and 1 minute is equal to 60 seconds. So this is equal to 0.00183 kilogram per second. Just convert the kilogram per hour and kilogram per minute into kilogram per second. Now mass flow rate of condensate is equal to mass of steam minus mass of air cooled. Mass of steam minus mass of vapor. It means that condensate means that from this point, from this, here is dry saturated, here is steam is dry saturated, and here this is liquid. So from this point to this point, so here mass flow rate is 5.55, and at 29 here the mass flow rate is 0.00. So condensate is from this point to this point. So mass of condensate or mass of steam dry saturated minus mass of vapor at this point. So which is equal to mass of steam N is basically equal to 5.555 kilogram per second minus 0.00183 kilogram per second. So mass of condensate is equal to 5.55317 kilogram per second. Now we know that heat rejected is equal to mass of condensate multiplied by latent heat of vapor. This is basically latent heat of vaporization. And we know that here enthalpy is HF and this is Hg, and Hg minus HF is equal to HFg. So from this point to this point, the difference is basically latent heat of vaporization. So heat rejected is equal to mass of condensate or mass flow rate of condensate multiplied by latent heat of vaporization. So first we find HFg. So from saturated steam table at temperature is equal to 36.2 degrees centigrade. This is latent heat. So at this temperature the steam is dry saturated. Therefore we use this value because here steam is dry saturated. Now 36.2 is not available, so from steam table temperature in degree centigrade and HFG in kilojoule per kilogram. So in steam table 36 and 40, sorry 35 and 40 are available. We have to find the value at 36.2. So at 35 and 40 the value of HFG are here from the steam table. At 35 the value of HFG, this is 2418.62, 2418.62, and this value is 40, 2406.72, and we will interpolate between these two values. At 35 the HFG is 2418.62 and at 40 this is 2406.72. So at 35 degree centigrade HFG is 2418.62 and at 40 HFG is 2406.72, and we have to find HFG here. Interpolate. So by interpolation, third value minus first value divided by third value minus second value is equal to third value minus first value divided by third value minus second value. So from here HFG is equal to, calculate this, so HFG is equal to 2415.764 kilojoule per kilogram. Now we can easily find heat rejected. So Q dot is equal to m dot mass flow rate of condensate multiplied by latent heat of vaporization. So Q dot is equal to m dot of condenser is equal to 5.55317 kilogram per second, and HFG is equal to 2415.764 kilojoule per kilogram. So Q dot, multiply these two value, which is equal to 13145, and kilogram is cancel is kilogram, so this is kilo, and joule per second is equal to watt. So this is heat rejected. So this is the end of the problem, and for more problems please like and subscribe my YouTube channel and share with your friends. Thank you.